a given point. This would be my R of t. I know the direction of R prime is tangential. What I don't know is how long it is. So I'm just going to draw in what might be R prime. If I draw in, does that show up? Yeah. If I go to draw in t, t is defined to be r prime divided by the magnitude of r prime.
So then a green pen would be a little bit darker.
Oh. Yeah, thank you. Watch it be too dark. Okay, so t is r prime divided by its magnitude. That means that t has the same direction as r prime, but its length is 1. I don't have any scale here, so I can't tell you what length of 1 is. I'll call this length 1 and label this guy T of T. It's got to point in the same direction as r prime. Now what about n? N dotted with t is 0. Therefore, it's orthogonal. There are 2 possible orthogonal directions. One is going to go this way, one goes this way. Without any explanation, I'll tell you that T points in the direction the curve is turning. So at this point, my curve is starting to turn this way. This is going to be n. I don't know what length 1 is, but t and n have to have the same length because they're both length 1. So if I give you a curve like this and I fix a point and I say sketch in t and n at that point, I'm not going to sit there and take a ruler out and say you're a tenth of a centimeter off or something. But I'm looking for the correct directions and that they're as good as you can get to the same length. If I look at another point over here, then my t here, I'll try and roughly keep it about the same length, is going to look like this. And N is going to point in the direction, kind of in the concave down direction. And it's going to look like this.
So is N always going to point like within the curve?
Yeah,
Okay.
it's always going to point to the inside. So if I pick a point here, so I'm coming around this way, my T is tangential, and to the best of my ability to draw, I'm trying to keep these all the same length. Now R prime is going to vary. It might be really short here, it might be really long here, I don't really care. N is going to point this way. Okay? Now, at each point in this circle, there's a circle of, or excuse me, at each point along the curve, there's actually a circle of best fit. Okay? It's called the osculating circle. We're not going to compute with it. I'm not going to ask you about it. We don't have the time. But if I were to draw this line in the normal direction, the center of this circle would lie along that normal line, and its radius would be 1 over the curvature. So where the curvature is relatively small, that circle of best fit is going to be big. And where you have a real tight curve, like if you have something like this, the circle of best fit is going to be very small. Here, the circle of best fit is going to be relatively large. It's called the osculating circle. And you can have exercises which will ask you, compute the curvature. That circle of best fit has a radius, which is the reciprocal of the curvature, and you move that distance along this line, you get its center. Okay? So just like you talked about tangent lines giving you localized fits to curves, you can also talk about circles fitting up to a curve. Okay? Now, what do we want from this? What we want is, I want to notice that V is my velocity. So this would be R prime of T. A is acceleration. And that would be either the first derivative of velocity or the second derivative of R. And the question is, how does acceleration fit into this picture? So R is giving me position. It tells me at any given point in time, where am I on this curve? R prime gives me velocity. The magnitude of R prime is the same thing as the magnitude of velocity, and we call that speed, just magnitude of velocity. This is speed. Acceleration looks at the rate of change in the velocity. It's going to take into account both changes, rates of change in the velocity vector's length as well as direction. The question is, how does acceleration fit into this picture? It's not necessarily orthogonal to n or t.
Because it is a unit vector to it.
Acceleration is not going to be unit. These aren't necessarily going to be acceleration vectors, but acceleration will lie. If I have a curve like this, okay, at any given point, you can sketch in the tangent line. The acceleration vector is going to lie beneath that line. Beneath it, it's hard if it was in 3 dimensions, but it's going to point in one of those kinds of directions. Now, it might point down, it might point tangential, but you'll never get an acceleration vector pointing up this way. Okay? The acceleration vector, what people like to do with it is, so on this picture, I have my unit tangential. This direction is my unit normal. And typically what people do is they project A onto both N and T. N and T are unit vectors. So if, for instance, I had acceleration coming down here, and I go to project the acceleration in the tangential direction, I drop a perpendicular down, and this would be the component of acceleration, or its length would be the component of acceleration in the tangential direction. And if I projected A onto N, I'd extend this line, drop a perpendicular down, and this would be the projection of A onto N. You guys see it? So these are those pictures that one really needs to know. And notice what happens if I add this to this, I get A back. What I need to know once I have T is how long is this vector? And how long is this vector? So to summarize this, we write A as a number times T plus a number times N. And these numbers are the scalar projections of acceleration onto T and N. Well, this is going to be obnoxious to compute with. It's a messy formula to get the projections out. That's just if we have two vectors randomly chosen. These vectors, N and T, they're obnoxious to compute to begin with. So what do? The usual. Somebody does a lot of fiddling around, and it is a given that the scalar projection of acceleration onto T is V prime of T. Okay, now be very careful. V of T is the magnitude of the velocity. Magnitude is a scalar. This is the derivative of that. Okay? So, V of T is speed. We end up with V prime being the scalar projection of A onto T. And we get the scalar projection of acceleration onto the normal vector to be curvature A of T times V of T, the speed, squared. The book will call this A sub T, and they'll call this whole thing A sub N. And again, these are not going to be formulas you have to memorize. I'll supply them. Let me try and indicate what becomes important here. A of T is equal to V prime of T multiplying the tangential, the unit tangential, plus the curvature at a given point times the square of the speed. That's in the normal direction. All right. Curvature, is it positive? Can it be negative? Go back and think of definitions of
The line has a
curvature.
curvature of 0, so no.
Hmm?
The line has a curvature of 0.
Well, but in general, can I ever have negative curvature?
We have the absolute value.
There's absolute values all through there in magnitude. If you look at definition of curvature, whatever it is I defined it, here, curvature, magnitude, that's positive, magnitude, that's positive. Curvature, always positive. And remember, v of t is the magnitude of the velocity vector. Regardless of whether v of t is positive, well, v of t is always positive, but maybe it's 0, but you square it.
Why is v prime of t multiplied by t?
It's not multiplied, it's v prime of t.
Yeah, but then you've got another t next to it.
That's the unit change. in the
That's a vector, yeah,
Oh,
That
that's
first part
magnitude,
is
pt.
the
Okay.
scalar number that goes.
That's
yeah,
right.
okay. So this here is also positive. What about v prime? Both of these might be 0.
Positive or negative depending on the path.
Yeah.
Yeah, I mean, if I'm speeding up, increasing the magnitude of the velocity, v prime is an increasing function, so its derivative is positive. On the other hand, if I'm slowing down, v prime is negative. And if I've got cruise control on,
No acceleration.
no, I can have acceleration,
If you're going.
but it's gonna all be in the normal direction. Okay, so if there is no change in the speed, v prime is equal to 0, and all of A is in the normal direction. So in terms of the projections, the work, the obnoxious stuff is done for you in terms of computing the value of those projections. What this means in terms of a curve, well, take a look. If I look at a given R, and I have R prime, actually it's probably a bad picture to illustrate what's going on. So let me, if I have a picture that looks like this, here's a given RT. Have the direction going like this. So my R prime is maybe even in the same direction as R. It's very close to it. If I go to put in T and N, the tangential vector is going to point in the same direction as R prime. But it's going to be length 1 without a scale. I don't know what that is. I mean, for all I know, length 1 is way out to here. But if I label this T and I go to put in N, I'm going to try and keep N at the same length. So that's going to be my N, and it's at right angles here. You look at the formula for acceleration. Acceleration is v prime times the vector t, so that's the projection in the t direction, plus k v squared in the normal direction. Okay. If I'm telling you that I slow down, well, here, let me draw in a couple different vectors. So let me call this A1. Let me call this vector A2. Let me call this vector here A3. Let me call this vector A4. Okay. Scenario 1, I'm speeding up. Which vector could be the acceleration?
It's gonna be A1.
If you're speeding up, v prime is positive. The component for n is always in the positive direction. Or excuse me, the component is always positive. But this is positive, and therefore acceleration is going to be generated by taking positive multiples of t and n and adding them together. A1. Can A4 be an acceleration?
You're sliding off the path.
No.
Okay. You can give me physical answers, but mathematically, what's telling me it can't be?
Normal's not towards the inside of the curve.
And what's telling me that, once we now have the formulas, what's telling me that this couldn't happen? What would be
You'd have
Per-
to have a negative normal and you don't.
yeah, well, not a negative, you'd have to have a negative component in
Yeah.
front of the normal. Because look, if this was your acceleration, the component in the normal direction is backwards. It's going back this way. It's going to have to be a negative multiple of n. And acceleration, its component in the n direction is never negative. Do you see what I'm saying? So, now. If I'm on cruise control, so that my speed is not changing. Now, this doesn't mean my velocity isn't changing, because maybe my direction changes. But velocity has two components, two parts to it. And if I tell you that speed's not changing, which vector
A2.
It's got to be A2 because that component in the tangential direction is 0. So all of the acceleration is in the normal direction. Finally, A3, what pulls me back, I've got to have, for the vector A3, a negative component in the tangential direction. Which means V prime has to be negative, which means slowing down. So we get a 3 out when we're slowing down because that makes V prime less than 0. This is the mathematical way to look at it. Now, you guys probably have a much better feel for the physical explanations. But everybody comes up against something for which you're not going to always have a good hands-on feel. And if you look at formulas as something more than just providing numbers out, you can say, I can see a lot of physics in this formulation. And I can understand a lot of acceleration in terms of the formulas that are given here. If you want to keep your acceleration from pulling too much in the normal direction, what makes this small? You're going to go into a curve. What keeps you from tipping over? Slower speed or
Different curve.
Straight.
small curvature to the extent of maybe 0 curvature, you move straight. So there's two ways you can make this small. One is keep your speed to a minimum, or don't go around curves. And if your speed is going to be high, you've got to really compensate by this, avoiding the curves, or worded another way, I guess. If you're going to be going around a really tight curve, if your speed's too big, you're going to tip over in the normal direction. I mean, I start to get mixed up as to which direction you actually tip, but the acceleration is pulling you too far this way. Okay? Okay, this is the central picture. So this takes us through 13.4. You can look at book problems. There are certainly problems in the book, and they may be on the list, that will ask you to do things like calculate the tangential vector. There's got to be stuff in here, must be in the prior section, where they ask you to compute and the normal vector